Hi. Here we are to find the difference in area between a square that's inscribed inside a circle and the outer circle. So it's actually the outer circle's area minus the inner square's area. And there's not much to figure out here with regards to algorithm. These are known formulas. So this video is going to be a little bit different than usual in that it's mainly going to be a symbolic reasoning in tacit APL. So first, a little bit of theory. We are going to find out what are the areas of these two components, the circle and the square. And what the input that we're given is the diameter of the outer circle. So if that's the diameter of the outer circle and the square inside is as big as possible, that means the square inside is exactly touching with its corners on the circle. It also means that the diameter of the circle is the diagonal in the square. It's a straight line that goes from one corner to the opposing corner diagonally. Okay, so with that in mind, we have the Pythagorean theorem that states that the square of the length of the longest side in a right-angled triangle is equal to the sum of the squares of the shorter sides. However, here we know it's a square, so the two shorter sides are identical in length. And now we're going to do this entirely symbolically. So let's do this with a comment. We're going to say that the square, which is the same thing as the multiplication of self, so multiplied by itself, of the diameter of the circle, which is the diagonal in the square, is equal to the sum of the squares of the smaller sides. But since they're the same, it is also the same as twice that. So if we take the squares of the smaller sides and multiply that by the constant 2, so this is a 2 that's made into a constant function, and we're multiplying that with the self-multiplication, which is the square, then the equality holds. Now, we don't actually want to compute it this direction. We want to go the other direction. We want to find the smaller sides such that we can compute the area, which is just the smaller sides multiplied by each other. Oh, but since they are identical, then the same thing as the square of the smaller side. And that's in fact what we're getting here. So in order to make this work, remember on the left, we had the term that represents the diameter or diagonal. And on the right is we have the squares for the smaller sides. All we need to do then is eliminate this doubling on the right. So we can do that by dividing by 2 on both sides. That eliminates this one. And instead, we divide by 2 constant on the left. This equal sign is not to be taken as a function here. We're just stating that these two things are equivalent. The diameter, diagonal, and of the circle, square, divided by the constant 2 is so the square of that diameter divided by the constant 2 gives us the square of the smaller sides. The square of the smaller sides, that is the area that we want. So this formula is what we need to apply to the original argument in order to get the area of the square. Okay, now we need to get the area of the circle. Here we don't use Pythagoras, we use Archimedes. And Archimedes says that given the diameter of a circle, the area of that circle is going to be pi times the square, so it's the self-multiplication again, divided by 4. It could also be stated simpler in terms of the radius, but given that we have given the diameter, this is what we get. Right. Then the next step is going to be to combine these two areas. We want the area of the circle minus the area of the square. And now we want to combine these two things. And we can observe a pattern here. But it's not exactly the same because we've got here the square of the argument divided by the constant 4 and the square divided by the constant 2. If we change this 2 into a 4, then we have made it half as big as it needs to be, but we can compensate by that by doubling it. And while we could write 2 times this, we can also observe the doubling, just like squaring is the self-multiplication, doubling is the self-addition. Right, now we have these two parts that are exactly the same. So we have, for whatever this gives, the square divided by 4, we have pi times that minus the doubling of that. So we can break out this part of the expression outside a parenthesis. Just take that part and we put it here, and then we apply pi times that minus twice that. And that gives us our finished formula, which is very elegant. And we can try it. And then we get the expected results. So, a very elegant formulation and an example of reasoning entirely in tacit APL. Thank you for watching.